Friends, let us continue our discussion on heterogeneous gas solid catalytic reactions, but this time let us bring in external mass transfer along with internal mass transfer playing an important role when the reaction is taking place. So, what we considered so far was a slab geometry catalyst, half width L, is a diffusion reaction and so on, but we assume that our concentration at the surface of the catalyst is the bulk concentration. So, now let us say that there is a external mass transfer resistance, and we will use film theory to characterize this external mass transfer resistance, which says that there is entire resistance to mass transfer is located in this boundary layer, mass transfer boundary layer, and beyond this point the concentration is the bulk concentration CAB. So, there is a diffusional resistance. So, there is a surface concentration, let us say CAI, we do not know what that concentration is, but this is how now the scenario will look like. That is, diffusion reaction, gas solid catalytic reaction in presence of internal diffusion resistances and in presence of external diffusional resistances. So, we are bringing now these two ideas together. Now, if we look at our mass balance within the catalyst, the balance is same as before. There is no change in the mass balance, because whatever has happened is in the changed condition that we have assumed now outside the surface of the catalyst. So, mass balance inside the catalyst is same, with boundary condition at Z equal to 0 being symmetric boundary condition, namely dCA dZ equal to 0. But now the boundary condition at Z equal to L, which earlier we said that concentration is CAB, now we are saying that that is not the bulk concentration, it is some concentration CAI, and which I do not know. So, I can't really use this as a boundary condition, but I do know that since the surface has no capacity to store mass, the flux of A coming from the bulk to the surface of the catalyst must be same as the flux of A going inside the catalyst, or in other words, if I call this Z equal to L, two sides of it minus and plus, then the flux of A at Z equal to L plus, that is coming from outside, must be same as the flux of A that is entering the catalyst surface. What is the flux of A L plus coming from outside? Earlier we used boundary condition film theory. So, this is the flux which is driving force CAB minus CAI multiplied by the mass transfer coefficient, and what is going inside is characterized by the diffusive flux. So, this must be equal to at Z equal to L. So, this gives me my boundary condition that I require for the solution of these mass balance equations. So, now I can make use of these two balances as well as the boundary condition, and in terms of our dimensionless quantities, we can once again write our mass balance equation as d square u d z star square as phi square u. I am assuming a first order reaction, and du dz star at Z equal to L equal to Biot number for mass transfer into 1 minus u at z star equal to 1 and du dz equal to 0 at z star equal to z star equal to 0. So, this is the symmetric condition at the boundary at the center point. This is the boundary condition. What is my Biot number? My Biot number, if you write everything in terms of mass transfer coefficient and so on, our Biot number works out to be kgl by dE. Kg is the mass transfer coefficient, external film mass transfer coefficient, L half width of the catalyst and dE the internal diffusion coefficient or DAE if you keep the notation same. This Biot number we can also write, keeping our tradition of writing it in terms of characteristic time, as L square by DAE divided by L by kg, and you can immediately see L square by DAE is same that we defined earlier, characteristic diffusion time Td, and L by kg is the characteristic external mass transfer time. This involves diffusion coefficient inside the catalyst pellet. So, that is DAE. This one is external mass transfer coefficient. So, Biot number actually characterizes what is the role played by diffusion, internal diffusion vis-a-vis the role played by the external diffusion. So, if Biot number is very large, very large, let us say larger than 10, that would mean that time for external diffusion, internal diffusion is time scales is very large compared to external time scales for external diffusion. So, Biot number tending to infinity would be the case when external mass transfer is not important, only internal diffusion is important. In fact, we could solve these mass balances with appropriate boundary condition and so on, and then write the solution for u as cos phi z star by phi by Biot number In fact, this is how concentration will vary, and you can immediately see when Biot number is tending to infinity, the solution u becomes cos phi z star by cos phi, which is the same solution if you do not consider external diffusion at all, and that is what we said just few minutes back. In fact, if we now define our effectiveness factor in the similar manner as we had defined earlier, that is the effectiveness factor as 1 over V R of Ca dVp or divided by R of Cab. For this particular case, we can simplify this solution as, or we can obtain this solution and write it as, for example, we can write eta g as, since we are considering only first order kinetics, we actually can write which upon rearrangement actually gives us Now, this particular solution is interesting because it further then we can write this as the inverse of effectiveness factor is 1 over or inverse of internal diffusion effectiveness factor, because if you recall tan phi by phi was the effectiveness factor if when we considered only diffusional resistance, internal diffusion. So, inverse of that plus phi square by Biot number by m. So, once again if Biot number is infinity, we get effectiveness factor same as internal diffusion resistance. Now, this is as far as single reaction in an catalytic gas solid catalytic reaction is concerned. Now, we see several other interesting results or implications if we have more than one reaction or multiple reaction. For example, if we look at typical example of multiple reactions such as A going to B going to C, the example shown here is butene going to butadiene to carbon dioxide, and what we see here on the x axis is the particle diameter and this is yield of butadiene, butadiene, and under identical conditions these experiments have been done, except the catalyst particle size is increased. Now, if you see typical result, what it shows is initially at lower particle ranges the yields are fairly constant, but as particle size increases the yield is actually decreasing of butadiene. That means, more and more butadiene is going to carbon dioxide, which otherwise stopped at butadiene level. Now, why should particle size matter? It matters because this is a catalytic reaction. Larger particle size imply diffusional resistances are stronger, and in this particular case increased diffusional resistances led to the reducing of yield. And in fact, that is precisely what is shown here for the reaction scheme such as A1 going to A2 going to A3, and what we have here is conversion and yield diagram. This is what we earlier had seen when we talked about kinetics. So, without any diffusion limitations, if this was a homogeneous reaction or even if it was a heterogeneous reaction, the diffusional limitations were not there, the yield conversion diagram was, for example, something like this. Now, same reaction, same conditions, but for some reason the diffusional resistances became important, such as particle size increasing. We see that under diffusional control regime the yield conversion diagram has now shifted, and in fact yield is generally lower under diffusional control regime compared to the reaction control regime. Now, why is this all happening? Although one can go into details of each one of the cases individually, I will just give you a broad outline as to what is happening. Now, let us go back to our reaction single reaction scenario, and we saw that, for example, if there is a reaction of a kind A going to B, and if this, let us say that this is a reaction is power law kinetics, then we saw if diffusional resistances are strong, we get N observed, which is N plus 1 by 2, and E observed, that is activation energy observed, is E by 2, or E observed is E by 2, the true activation energy by 2, and we saw this few sessions earlier. The point is that if you have a diffusional resistance, the dependency of rate on concentration is no longer the same as dictated by the true kinetics. Diffusional limitations falsify the kinetics and mask it. All right. Now, let us say that we have another reaction B going to C, which is following the kinetics Cb raised to m. So, we have a series reaction A going to B, B going to C, and depending upon the kinetic rate constants as well as order, the impact that diffusional limitations will have on this process will be different than the impact that diffusional limitations will have on this particular process. To give you a, illustrate this point, let us take a simple example. Let us just say that we are interested in looking at, if this is reaction 1 and this is reaction 2, what is the ratio of R1 to R2? Okay, or let me take simple example, because this example is also not simple enough for what I want to illustrate. So, what I am going to say is that instead of considering B going to C, I am going to consider a reaction C going to D, completely unrelated reaction, or A going to C if you want to relate it. So, let us say A going to C. So, we have reaction A going to B, A going to C. So, this is like a desired reaction, undesired reaction kind of scenario. So, let us say that we are interested in looking at R1 by R2. Now, R1 by R2, which will tell us the selectivity of B over C and so on, under diffusional control regime. So, this is under strong, let us say reaction control regime, this would have been simply K1 by K2. If we assume both M and N are same, that is orders are same. Now, the same thing, so let us call this selectivity. Same thing under diffusional limitations will be R1 observed by R2 observed, which in case diffusional limitations are very strong, I will have to write S observed as eta 1 into R1 divided by eta 2 into R2. Eta 1 and eta 2 are, let us say, respective effectiveness factors, which under strong diffusional limitations is phi 2 by phi 1 into R1 by R2. And if we now substitute our kinetic rate expression, that is R1 and so on, this now S observed becomes square root of K1 by K2. So, under no limitations of diffusion, selectivity was ratio of K1 by K2. Under strong diffusional limitations, it becomes square root of K1 by K2. So, selectivity of B over A, let us put some numbers. Let us say K1 was 9 times K2, was 9 under reaction control regime. Same selectivity under diffusion control regime would be square root 9 or 3, a clear indication that diffusivity is now reduced. I mean, diffusivity reduced the selectivity of the desired product. Mind you, here we did not do anything about order of reaction. We assume the order of reaction to be same. You can imagine the kind of results we will get if the order of reaction also itself is different, then what effect it will have on differing selectivities, yields and so on. We do not have enough time to go into details of all reaction schemes or at least simple reaction schemes. So, we will conclude this discussion of non-isothermal reaction by noting that when you have multiple reactions, the influence of on the desired reaction may be different than undesired reaction, and your selectivities, yields, all those could be very much different. Now, at this point, let us recap what we have seen so far. We said we will look at slab geometry, but then relax that constraint by looking at cylindrical and other geometries, and found that effectiveness factor relationship is fairly uniform. We said we will look at first order reaction, but we also looked at generalized kinetics, where you get Thiele modulus, which for example, in a power law kinetic situation depends on the bulk conditions and so on. We then said that we are considering only internal diffusion, but then relax that internal diffusion as well, and saw that if you have both external and internal diffusion, things could be different depending on the Thiele modulus as well as Biot number. Now, we also looked at what happens to the kinetics when diffusional limitations are important, and how do we find out whether they are important or not, by not knowing the true kinetics, but by just doing experiments, observing the Thiele modulus, and by looking at the value of this Thiele modulus, some judgment about the extent of diffusional limitations can be made. All this discussion was based on assuming isothermal situation. That means, your catalyst thermal conductivity is so large that if at all any heat is liberated, it is dissipated very fast. There is hardly any temperature change, or the heat effects with the reactions were itself very negligible. That is, the heat of reaction was let us say less than 4 kilocalories. I mean 4 is also fairly high number, less than 1 kilocalorie, practically negligible. So that you could observe any appreciable change. But in reality, that is not always the case, and we could have heat effects accompanied by the diffusional mass transfer effects, or in other words, not only mass transfer, but energy transfer also now becomes an important issue while looking at gas solid catalytic reactions. So, what essentially we are saying is that we have now our catalyst, and this time we will just focus on internal resistances. Again, slab geometry, everything is same. Concentration at the surface is bulk and it is decreasing. The temperature at the bulk is also Tb, and inside concentration is Ca, temperature is T, and it is either same or different. So, now we have to set up mass balance and energy balance equation to account for these temperature variations, so that we will know what is likely to happen as far as temperature inside the catalyst is concerned. So, let us write down our mass balance equation, which is same as before, because mass balance equation is a mass balance equation, and let us keep it in the form of rate which is we do not know what that rate is at the moment, but we will come back to that rate in just a minute. So, we are looking at our mass balance equation. Now, just as we have our mass balance equation, we also can write energy balance equation in a very similar manner, and we will end up with the following. Lambda E is the effective conductivity, thermal conductivity of this catalyst. Once again effective, because remember this catalyst is not all solid block of same material. So, you can't say that it is the thermal conductivity of a single material. It has the components of that material, but more importantly it has voids in which there is air, and air in general is a poor conductor. So, the thermal conductivity of the catalyst is several times less than the actual thermal conductivity of the catalytic material. So, therefore, the heat transfer resistances become important, because they are not good conductors of heat, or their conductivity is rather limited. Now, what are our boundary conditions? At z equal to 0, let us write down our boundary condition. At z equal to 0, the same condition as before, concentration is the bulk concentration, temperature is the bulk temperature at z equal to L, sorry, on the surface. What about z equal to 0? Symmetry, because same whatever we discussed about mass must also happen same similar manner about energy, because it is not that one end of the catalyst is insulated, the other one is exposed, both ends are exposed equally. So, dCA dZ must be 0, dt dZ must be 0. So, we have these two mass balance equations and the required boundary condition, and we can solve them, look at their solutions and so on. But before we look at their solutions, let's try to look at what is happening here. So, before we start looking at the solution of these equations, let us try to understand what is happening in this particular situation. Firstly, we have reaction which is causing the change in concentration of A. So, we have let us say we have rate of reaction which is a function of Ca and T. Now, concentration change is resulting into, or because of reaction there is a energy that is getting generated, and what is the rate at which this energy is getting generated is the heat of reaction times the rate of reaction. So, because the heat reaction is releasing heat and thermal conductivity is not very high, or it is rather limited, the temperature is changing. Now, because temperature is changing, the rate of reaction will change, because rate is function of both concentration and temperature, or in other words we have a feedback effect of this simultaneous variation of concentration and temperature, and this effect of, that is, the change in concentration and change in temperature are related to each other. Because why is temperature changing? Temperature is changing because heat that is generated. The heat that is generated depends on the rate of reaction. The rate of reaction also determines how concentration will change. So, in other words, how concentration changes and how temperature changes are related to each other, and we can mathematically see this relationship in these two mass balances itself. To be more precise, if we take these two mass balance equations and these two boundary conditions, we can actually write T minus T bulk as minus delta H, that is the heat of reaction, dAe by lambda E into CAB minus Ca. Or in other words, the concentration and temperature variations inside the catalyst pellet are actually related to each other. Now, what does this particular relationship implies? Let's look at this little more closely. We can also write this in the form T minus Tb divided by Tb as minus delta H, and the reason for this will become clear, into CAB 1 minus Ca by CAB divided by lambda E into bulk temperature. This quantity over here, if you look at its dimension, this is dimensionless, this is dimensionless. So, this number over here must be a dimensionless number, and it is indeed a dimensionless number given a notation beta and referred to as Prater number. Referred to as Prater number. Now, what is happening? We'll come back to that in just a minute, but let me then go ahead and say that we are going to now look at the solution of these two equations. But what has happened? We have these two mass balance equations, but in reality we do not need two mass balance equations, because we just now saw that temperature is related to concentration. So, we can in principle just consider mass balance equation let us say if we are considering a first order reaction, with the understanding that T is a function of concentration. What is that function? That is a linear, actually that is a linear relationship which we just now defined. That is dimensionless. In fact, if we work in terms of dimensionless quantities, that is, let us say we define T by Tb as dimensionless temperature V, and we have this dimensionless Prater number and our usual so if we define V as T by Tb, U as concentration Ca by Cab, then we have a nice equation V minus 1 is beta into 1 minus U, temperature in terms of concentration. Let us also try to see what is the implication of this relationship. Let us say what is this Prater number? What will happen if reaction goes to completion? If reaction goes to completion, this particular quantity will have its maximum value, namely 1. So, if reaction goes to completion, Ca is 0, so that means there is no more reaction. So, temperature cannot change further. So, in other words, beta is nothing but the maximum temperature change that can occur in a catalyst, because Ca value 0 is the minimum value. So, T minus Tb, that is delta T by Tb, non-dimensionless temperature difference, the maximum value of which is beta. So, beta has a significance that it represents the maximum temperature change that can occur because of energy and mass transfer limitations. Now, what happens to value of beta? For example, if the reaction is isothermal, heat effects are negligible, beta is 0. If it is an exothermic reaction, then we have delta H or heat of reaction which is negative, and so beta is positive. So, beta is greater than 0 for exothermic reaction and is less than 0 for endothermic reactions, because delta H is now positive. So, by according to definition of this Prater number, it is either positive or negative. So, now let us say that we make these equations dimensionless by using these dimensionless variables, and we can actually write our mass balance equation, because we need only one now. Say some function f, which we can write in terms of function of u alone, because temperature can be substituted by in terms of concentration, where this function f of u is e raised to gamma into u. Gamma is activation energy by RTB, another parameter that will come. This u came, remember our kinetics is R is equal to kV of T into Ca. So, this u comes dimensionless u because of concentration. This term you can identify with kV term, because if you assume Arrhenius rate form, you will get this kind of dependency on temperature, and all we have done is for dimensionless temperature we put the in terms of dimensionless concentration. So, these are our mass balances, and now let us we also define in a similar manner the effectiveness factor. Now, the only difference that we have to make here is that effectiveness factor, which is 1 over V p integral R Ca of dVp divided by both diffusional resistances and energy transfer resistances are negligible, what would be the rate? So, our rating now parameter is the observed rate to what rate would have been if none of the diffusional limitations or energy limitations were present in the system. So, one can actually numerically solve, it is not possible to solve it analytically, but let us look at the solution of this equation. So, what we are seeing here is actually the effectiveness factor for first order reaction in a spherical catalyst, but if it is a cylindrical or sphere or slab, we know the results are similar. So, what we see here is Thiele modulus and effectiveness factor eta for a given value of gamma equal to 20, because now effectiveness factor is a function of Thiele modulus, gamma and beta. Gamma is E by RTB and beta, as you know, we said that it is a maximum temperature temperature rise. So, what we see here is for different value of beta. So, for example, this is a solution for beta of 0.8, this one over here is for beta of minus 0.8, and these are values going from 0.8 at one extreme to minus 0.8 at other extreme. So, we have these different values. Somewhere in the middle is the solution when beta is 0, that is what our isothermal case is. So, now if we look at this behavior of non-isothermal pellet, I will just put on the side a typical sketch for isothermal, which we had seen earlier, eta versus phi, and this was about 0.3 and somewhere 3 over here. We see that there are some differences and similarities. Of course, when beta is equal to 0, this is what the solution is. So, it is no surprise that it is similar. In fact, for all beta values negative, the solutions are almost similar to that. In fact, they are lower and lower as the beta value becomes negative. That means, reaction is highly endothermic, it is more endothermic, the beta value will be higher in magnitude with a negative sign. So, effectiveness factor is actually decreasing. So, diffusional resistances influence or energy transport resistances, for example, influence the endothermic reactions in a severe manner, because compared to no energy transport limitations, the effectiveness factors are lower as we are getting endothermic reactions. But the situation is completely different when we look at what happens when we have exothermic reactions. For exothermic reactions, in fact, this is the boundary 1. For quite a few cases, this entire region, the effectiveness factor is greater than unity. What does this imply? Remember, we had defined our effectiveness factor as R observed divided by R if no limitations existed. Now, this value being less than 1 is understandable, because if there are no limitations of mass or energy transport, you get the highest rate. I mean, that is a normal thinking. But look at what happens, and that is indeed what happens when you have endothermic reaction. But look at what is happening when you have exothermic reaction. When you have exothermic reaction, having mass transfer limitation is actually enhancing the reaction rate. Why is that? That is because you have, I mean, how do we know that? That is because effectiveness factor is greater than unity. Effectiveness factor is greater than unity if the reaction is exothermic and we have reaction rates inside the catalyst pellet or the average of those higher than. Now, why is this happening? To see that, let us go back to our and look at what is actually happening here. Remember, our rate is a function of concentration and temperature. Now, if reaction is exothermic, temperatures are higher than the bulk by depending on. So, this is the temperature inside the catalyst, this is the bulk and its value is high. Concentration is always lower than the bulk. So, if this is the bulk value, the concentration here is always low than the bulk. But look at what is happening to temperature. Temperature inside the catalyst pellet will be higher than the bulk temperature if there are heat transfer resistances. So, what does that do? Inside the catalyst pellet, temperature is higher, and remember how temperature dictates rate of reaction. Arrhenius rate dependency, highly non-linear. So, increase in temperature, we saw that example I think in the beginning. A 10-degree increase can double or triple your reaction rate or change it by several order of magnitude, depending on the activation energy, of course. So, if the temperature inside is higher than the bulk condition, the rate of reaction inside is also higher than the bulk condition if the reaction is exothermic, and hence the effectiveness factor or the observed rate can be higher than the rate in absence of energy and mass transfer limitations. So, this is one clear advantage of having energy and mass transfer limitations if reaction is exothermic. We can argue the same thing if reaction is endothermic, temperature inside the reactor, inside the catalyst will be lower than the bulk. So, not only the concentration will be lower, but temperature also will be lower, implying that the rate of reaction inside the catalyst pellet will be low, both because of concentration and temperature being low. So, making situation worse than not having the same temperature as bulk. So, endothermic reactions suffer because of mass and energy transfer limitations, and exothermic reactions may benefit if there are in mass and energy transport transport limitations. So, this is just to give you an idea as to what happens when we have these exothermic non-isothermal situations. There is one small point which we will try to cover, because if you look at what happens is actually there is a possibility of multiple steady states in a catalyst, and we will concentrate on that in our next session before moving further. Thank you.